The Earth is the only rocky planet in the Solar System with a large natural satellite, the Moon. Mercury and Venus don't have any. Mars has two small irregularly shaped satellites that actually resemble asteroids more than planetary bodies. The Moon, however, is a true satellite with significant dimensions when compared to the Earth. It is larger than all the dwarf planets in the Solar System, and some refer to the Earth-Moon system as a double planet. In fact, the influence of the Moon on our planet is so strong that it might have contributed to keeping it habitable for a long time by stabilizing the tilt of the Earth's rotational axis. It is important to understand if the fact that the Earth has such a large moon is something exceptional or common for other planets in our galaxy. But to understand this, we first need to discover how the Moon was formed. What do we know about the formation of the Moon? Let's try to understand it. The first modern hypothesis about the formation of the Moon was proposed by George Darwin, the son of a much more famous Darwin, Charles Darwin. George Darwin, in 1879, suggested that the Moon might have formed through an expulsion by the Earth. Darwin imagined that, in the early phase of Earth's life, it rotated very quickly around its own axis and was still not completely solid. The centrifugal effect of Earth's rotation would have caused a part of the Earth's material to be thrown out, which would then go into orbit forming our satellite, the Moon. This idea was predominant and remained very popular until about the mid-20th century, but was later abandoned. Today we know it does not adequately explain the observations, particularly because the Earth's rotation would have had to be extremely rapid to allow for such an effect. Additionally, if the Moon had been expelled by centrifugal force, its orbit should be aligned with the Earth's equator, which it is not. Another proposed possibility is that the Moon was captured by the Earth, meaning it was an independent celestial body that later entered Earth's orbit. This explanation is not impossible but is considered very unlikely. It is difficult for a planet to capture such a large celestial body, and the orbital parameters would have to be very finely tuned. Additionally, there would need to be a mechanism explaining how the speed of the captured body, that is, the Moon, was slowed and braked by the Earth. In short, a hard-to-achieve mechanism. Furthermore, it doesn't explain a crucial observation. The analysis of lunar rocks brought back by the Apollo missions showed that these rocks have an isotopic content almost identical to that of terrestrial rocks. The abundance of isotopes is a very precise signature of the origin of a rock, and the fact that the isotopes are so similar suggests that the Moon and the Earth had a common origin, meaning the capture hypothesis does not explain this observation well. One could imagine that the Moon and the Earth formed in the same way, in the same region of the Solar System, independently but simultaneously. Essentially, we start from a flattened disk surrounding the star that contains material. This material aggregates over time until planetesimals form, which then, through collisions, form planets. Thus, the Earth and the Moon could have formed in the same area of the planetary disk and from the same material, explaining the same isotopic composition. However, there are two facts that suggest it didn't happen this way. The first is that the Moon has a very small internal metal core, while the Earth has a rather significant metal core, suggesting they didn't form from the same material. The second is the angular momentum of the Earth-Moon system, which is very large. The prevailing hypothesis today is that the Moon formed through a giant impact, a devastating collision that occurred about 4.5 billion years ago when the Earth was still forming. It is thought that another object the size of Mars collided with the Earth, releasing a large amount of debris and material that went into orbit, eventually forming the Moon. This idea might seem fanciful, but it is supported by the fact that during the early stages of the Solar System's formation, collisions between planetesimals forming the planets were occurring. Computer simulations have shown that an impact between the forming Earth and an object the size of Mars, called Theia, can indeed form a satellite like the Moon. This giant impact scenario explains a series of observations that other hypotheses do not adequately explain. For example, the large angular momentum of the Earth-Moon system, the small size of the Moon's metal core, and the fact that the Moon does not contain many volatile elements. Additionally, Earth has a higher density than the other rocky planets in the Solar System, which could be explained by the fact that it incorporated Theia's metal core. Although the giant impact scenario works broadly, many details are still not well understood. For example, the dynamics of the impact and the identical isotopic composition of the Earth and the Moon. Increasingly accurate simulations and future space missions that bring back more lunar samples might help to better clarify this dynamic. Ultimately, the goal is to understand whether the fact that a planet like Earth has a satellite as large as the Moon is common in the rest of the universe, and whether this might have a significant effect on the long-term habitability of a planet. Thanks for watching. If you enjoyed the video, please like and subscribe to the channel to support us.